Log on, tune in, find out. Another good idea from Cambridge.
Okay, thank you very much, David, and thank you to the Institute and to the program organizers for this opportunity. It's a wonderful opportunity. As David mentioned, it's a special talk, so if you're expecting a talk on computer experiments, that's not what this is. In fact, I was asked to prepare a talk for a general mathematical audience, and I hope I have accomplished that, which does mean that if there are experts in the audience, that maybe some of the things are a little bit boring to you. So I hope you can still find something to enjoy in the talk. So it's an overview of orthogonal arrays, and it's a very selective overview because there's so much work that has been done on orthogonal arrays. There are only a few things that I can touch on, and I will try to highlight some of the things that I think are important. They're not necessarily novel. I mean, they're not necessarily new things. Some of these have been around for a long time. I do try to point out along the way some open research problems. So if anybody has any interest in doing some research in that area, maybe you see some problems that you're interested in. Here are a few starting points if you are interested in orthogonal arrays, and some of you will be familiar with them. First of all, the library that Niels Sloan has on his website. It's an extensive library, not just on orthogonal arrays, but also on many other things. If you're interested in Hadamard matrices, if you're interested in integer sequences, all kinds of things you can find there. But there's a lot of information about orthogonal arrays. There's a second library on orthogonal arrays maintained by Warren Kuhfeld at SAS. It's more restrictive. It's only on orthogonal arrays of strength 2. But it's a little bit more up-to-date, actually, on orthogonal arrays of strength 2 than Niels Sloan's webpage is. So you can find some arrays in this webpage that you can't find in Niels' webpage. And then, well, it's getting a little bit old, 1999, but you know, I said it's a starting point. There's a book on orthogonal arrays, and I think there's a lot of material in that book. The book still gets quite a few references these days, and so as a starting point, it's still a good place to go to. And as I said, there are many references. I will mention some of them during the talk, but it's a very incomplete list that I'm going to mention. There are too many things. I know I'm going to run out of time. I know I'm going to fight with this little thing over there, but I decided to put a lot of things in here so that even if I run out of time, I mean, this will be available for you to look at, so you can go through it yourself at some later time. So I'll start with a brief introduction of what orthogonal arrays are, so that somebody who doesn't know what an orthogonal array is still gets a good starting point. So here's the definition of an orthogonal array. An orthogonal array of strength T with n rows, k columns, and based on s symbols is an n by k array with entries from a set of s elements, let's say 0 through s minus 1. So that if you take a subarray, or consisting of t columns, an n by t subarray, then in the rows of that subarray, you see every possible combination of those symbols equally often. So every t tuple of the symbols should come equally often as a row. And this is true for any t columns that you take, not just for a particular set of t columns, but for every selection of t columns. And let's say that you see every t tuple lambda times, and then lambda is called the index of that orthogonal array, and it's clear that the number of rows, capital N, must be a multiple of s to the power t. This is the common notation that I will use. So the number of rows, the number of columns, number of symbols, and the strength. And occasionally I switch notation, number of rows, number of columns with this as the number of symbols and the strength. These orthogonal arrays were introduced by C.R. Rao back in the 40s, mainly for use in fractional factorial experiments, and I'll just say a few words about that later on, but won't spend much time on the application necessarily. There are lots of different names for these symbols. The number of rows is also called Laplace combinations or number of runs. Number of columns is also known as the number of constraints or the number of factors. Number of symbols is also known as the number of levels. And then we have T for the strength, and that's pretty much the terminology that's always being used. I'm going to try to stick to rows, columns, symbols, and strength, but as a statistician, I'm actually more used to runs, vectors, levels, and strength, so I may slip up now and then. As I said, they're primarily used in factorial experiments, where you think of these columns as the factors in your experiment, where these symbols are the levels for the factors, each factor at s different levels, and where every row corresponds to a level combination that you're going to use in your experiment. So you don't use all possible level combinations, you tend to use just a subset of all possible level combinations, and the ones that you use are the ones that are given to you by this orthogonal array. The strength of the orthogonal array is, in statistics, related to the estimability of parameters under certain models, and I will say a little bit more about that in just a moment. But so the only thing I want to point out here is that it has some statistical meaning, and we come back to that in just a moment. What is orthogonal about orthogonal arrays? Maybe if you just look at the definition, maybe there's more a concept of balance here, and everything has to come equally often. So I'll come back to that as well, why these things are called orthogonal arrays. So here's a small example. This is an orthogonal array with 8 rows, 4 columns, 2 symbols for each of the columns, and it's of strength 3, meaning that if you pick 3 columns, and I don't know whether you can see the blue or not, but the first, third, and fourth column here are in blue, and if you look at all the level combination or the combinations that you see, 0, 0, 0, 0, 1, 1, 0, 0, 1, etc., you see every combination exactly once. And that's true for these 3 columns, that's true for any other 3 columns as well. That's what makes an orthogonal array of strength 3. It doesn't take much to see that an orthogonal array of strength t is also an orthogonal array of strength t prime if t prime is less than or equal to t. It also doesn't take much to see that these arrays are invariant under a number of different permutations. If you permute the rows, for example, the orthogonal array stays an orthogonal array. If you permute the columns, the orthogonal array stays an orthogonal array. If you permute the symbols within a column, the orthogonal array stays an orthogonal array. And 2 arrays where one can be obtained from the other by a sequence of such permutations, they're called isomorphic. So there's a fairly important research area to try to identify the non-isomorphic orthogonal arrays for a particular set of parameters, which is a pretty difficult problem. If time permits, I'll come back to that and say a little bit more about that later on. There are all kinds of construction methods for orthogonal arrays. One that I wanted to point out is what you see over here. If you have an orthogonal array with these parameters, then immediately you can also get an orthogonal array with these parameters, and the way you do that is by what is shown over here. Since there's invariance to permutations of the rows, you can always write this orthogonal array here in such a way that the first column is in this natural order, first the zeros and then the ones and then up to the s minus 1s. And then you simply pick this subarray here that corresponds to the zeros in the first column. You drop that first column, only keep this subarray over here, and you can easily check that it has these parameters. And that's important for something that I'll talk about in just a moment. This is, in some sense, a construction where you start with a larger orthogonal array and you come to a smaller orthogonal array. Of course, usually you're interested in doing it exactly the other way around, to start with a small orthogonal array and make something bigger out of that. And there are many constructions that do that. I will talk about a few constructions in just a moment, but not about all that many. Well, here are some basic questions about orthogonal arrays. Because the most basic one is, for which n, k, s, and t do these things exist? What do I need? When can I find such a thing? It's a very general question, and you can specify those questions a little bit. And so I have 2 reformulations here. And the first one says, if you tell me what the number of rows is, the number of symbols, and the strength, what is the maximum number of columns that I can obtain so that I can form an orthogonal array with these parameters? Because I'm really only interested in the maximum number of columns, because I have another number of columns. If I know the maximum, I can drop a column and then I get other numbers of columns. So really what I want to know is the maximum number of columns. So that's one reformulation here. A second reformulation is, I'll tell you how many columns I'm going to have, k, what the number of symbols is, what the strength is going to be, can you now tell me what the minimum number of rows needed is to construct an orthogonal array? So that's the second reformulation of the basic existence question. This maximum number of columns, it's denoted by this function little f, lowercase f, and the minimum number of runs is denoted by the function uppercase f. As you might expect, there are relationships between these two functions. I've written them up over here, and you don't have to memorize them, but the only thing I want to point out is that if I know all the values of the lowercase f function, then this tells me I can find all the values of the uppercase f function. Vice versa, that is not true. Even if I know all the values for the uppercase f function, I only get upper bounds for my lowercase f function. So if I really want to tackle this problem over here, knowing the values of the uppercase f is not going to give me the answers, not all the answers. Knowing the function lowercase f, that is going to give me all of the answers. So from that perspective, it makes sense to study the function lowercase f rather than the function uppercase f. On the other hand, there's so many parameters where we don't know what either one of those functions is, so any information that we can get is useful information, so you might, there's not much loss by studying both of those functions. So how do you establish values for those functions? Well, typically you find bounds in some way, and then obtain constructions of orthogonal arrays that attain those bounds. That's how you establish values for those functions. But as I said, many values are still unknown. There are two fairly general bounds, or at least two, for orthogonal arrays. One is referred to as Rouse inequalities, and the other one is called the linear programming bound. And I will talk about both of those. There are many methods of construction, and I will talk only about some of those. There are especially many methods if S is a prime or a prime power. If S is not a prime or a prime power, then there are not very many methods, and then you probably, most of the time, you're out of luck in trying to come up with orthogonal arrays. So coming back to this question, what is orthogonal about an orthogonal array? So here's kind of a mathematical answer. If you take a set of s minus 1 orthogonal polynomials on 0 to s minus 1, where the degree of the ith polynomial is equal to I, so they're also orthogonal to the constant polynomial, to the polynomial of degree 0. And if you then start with an orthogonal array, and within that orthogonal array, every symbol u, you replace it by this row vector, the values of u at these orthogonal polynomials. So you expand the number of columns of your orthogonal array. Every column is being replaced by s minus 1 columns, where these s minus 1 columns simply have the value of this orthogonal polynomial at whatever the entry of the orthogonal array was. So if you do that, then you can show that the matrix that you built that way is a matrix which has all of its columns orthogonal. And you can add a constant column to it, column of all ones. You can add that to it as well. All those columns are orthogonal. And of course, if you do that, you get this many columns. You get the column of all ones, and then for every column that you had in your orthogonal array, you replace it by s minus 1 columns. So you get k times s minus 1 columns from that replacement. And since they're all orthogonal, that means that the rank of that matrix that you have built has to be at least equal to this number, or has to be equal to this number. And the number of rows, of course, has to be at least equal to that number then. So n has to be more than or equal to 1 plus k times s minus 1. And that's exactly Rouse inequality for an orthogonal array of strength 2. You can think about this in statistical terms, and for those of you who are familiar with it, in terms of fitting a main effects model. So you have s minus 1 degrees of freedom for the main effects, for each of the main effects, and you have this intercept term, and all of these, if you use the main effects model, all of the contrasts corresponding to these main effects, to these the s minus 1 degrees of freedom corresponding to each of the main effects, they're all estimable, and so this is the number of estimable functions that you have, and they're orthogonally estimable actually, and so the number of observations that you have must be at least equal to this number. So that's Rouse inequality for orthogonal arrays of strength 2. If you talk about orthogonal arrays of strength 3, then you would go back to this picture over here. So I have an orthogonal array of strength 3 now. From that I construct a new orthogonal array of strength 2. To that orthogonal array of strength 2, I apply the bound that I just found. For arrays of strength 2, I apply this bound, and then after a little algebra, what you get is a bound for arrays of strength 3 that looks like this. Orthogonal arrays of strength 4, well, it turns out now you can even build a bigger matrix. You can add more columns to the matrix that you just built. Not only do you have the column with all ones and the columns corresponding to all these main effects, but now you can actually add columns to it corresponding to interaction effects. And so for every 2 columns that you pick, for every possible interactions of 2 of those columns, you have s minus 1 times s minus 1 squared functions that you can add to it. So it's s minus 1 squared columns that you can add to for every 2 columns that you pick. So the number of columns that you can add is k choose 2 times s minus 1 squared. And it turns out you can prove that all of those columns will be orthogonal, and hence the rank of that matrix must be equal to this number, and so the number of rows of the matrix must be at least equal to that number. So that would be Rouse inequality for orthogonal arrays of strength 4. And here are the general forms for even strength and for odd strength. And it's a very nice inequality, I think. I mean, it's very explicit, very simple form. They are sometimes very sharp. Sometimes you cannot improve them. There are other cases where they can be improved. But it's always a good starting point if you're wondering whether an orthogonal array exists or not. It's always a good starting point to go to these inequalities and see whether they're satisfied or not. And if they're not satisfied, then you can forget about it. Okay, so improvements are possible for some parameters. So let's say a little bit more about constructions and about the bounds. The simplest construction of an orthogonal array is probably the zero-sum array. And what you do is you take an s to the t by t array, that's what you start with, consisting of all possible t tuples based on the elements 0 to s minus 1. Right? So the s to the t of them, that's why you wind up with s to the t rows, and they're t tuples, so every row is of length t. So it's an s to the t by t matrix. And you add 1 column to it. And you add that column so that in every row, if you add elements up, they add to 0 modulo s. If you do that, you can show that's an orthogonal array. It's an orthogonal array with, well, you started out with t columns, you added 1 to it, so you have t plus 1 columns. You still have s to the t rows. You have s symbols, and it turns out to be a strength t. Very simple. Everybody can do it. You just have to be able to add up, and so everybody can do this. And you would expect perhaps that something that's that simple can be very good. Sometimes it is not very good, but there are some cases where it's actually the best you can do. Turns out that if the number of symbols is no more than the strength, then this number t plus 1 here is actually the maximum number of columns that is possible. You can't do any better than that. On the other hand, if s is larger than the strength, then you can do better. And that's what a method by Bush does, and I'm not going to talk about it in detail, but many of these methods use Galois fields or finite projective geometries. This method does too. It uses polynomials of degree up to t minus 1 and over Galois fields. So this only works if s is a prime power. And what this method allows you to do is construct an array with s plus 1 columns. And sometimes you can actually add a column to that. You can go to s plus 2 for some special cases where strength is 3 and s is a power of 2. But s plus 1, of course, is bigger than t plus 1 if you're in a situation that s is more than or equal to t. So this does better than the simple construction that we looked at just a moment ago. Now, whether this is the best that one can do is a question that's still open. There's a conjecture It's called the conjecture for orthogonal arrays of index unity, because as you may have noticed, all these arrays are index unity. Yeah, this s to the t, that's the smallest possible number for the number of rows if you're talking about an orthogonal array of strength t, so that's why they have index unity. So the conjecture is that the maximum number of columns that you can have in such an orthogonal array is t plus 1 if t is more than or equal to s, and this is not really a conjecture, this is what I just told you here, that's true, we know that that's true. This here is a conjecture that if s is bigger than t, then it's going to be s plus 1. We know that we can do at least s plus 1 through this construction, but there's possibility that we could do better than s plus 1, except nobody knows how. With the exception of two cases, with the exception of the case where you're talking about an orthogonal array s cubed s, and this t should be a 3 over here. Then we know that we can do s plus 2, and we know that that's the best. And in the situation that you have an orthogonal array of strength s minus 1 with s to the s minus 1 rows, then the conjecture is that s plus 2 is the best. We know that we can construct an array with s plus 2 here. We don't know whether it's the best possible orthogonal array. So there are situations here in this conjecture, the s plus 2 here, maybe that could be improved. The s plus 1, maybe that could be improved, but the conjecture is that it cannot. So that's an open problem, but it's probably a pretty hard one. I'll show you some easier ones later on. One more construction, the Rao-Hamming arrays. They are orthogonal arrays of strength 2, and I lost it. Right? So they are orthogonal arrays of strength 2. With s to the n for some number n more than or equal to 2, with s to the n rows, and s to the n minus 1 divided by s minus 1 columns. And that number is actually exactly equal to the bound in Rao's inequalities. So you get exactly the maximum number. You know that that's going to be the maximum number, hence you know the function lowercase f for s to the n s2 is exactly equal to that number of columns in these orthogonal arrays. They can only be constructed, or we only know a construction for these if s is a prime power. And there are many different constructions. You see one given over here. It's a fairly simple construction. You start with an s to the n by n matrix that consists of all n tuples over g of s. So the rows are simply all the n tuples over g of s. There are s to the n of them, obviously. So you get n columns that way. And what you do now is you take all the linear combinations of those columns, except you don't take linear combinations where all of these coefficients are equal to 0, and the ones that you take, the first non-zero coefficient should be equal to 1. Those are the linear combinations that you take, and it's easy to count. There are exactly this many of them, and it's also then easy to check that what you get is indeed an orthogonal array of strength 2. So it's again a very simple construction. There are other constructions that for this particular array. But these are pretty popular arrays that not only came up in statistics, but also in coding theory. And that's what I want to talk about next, the relationship between orthogonal arrays and coding theory. So somebody in coding theory looks at this in a slightly different way. I'm showing you the same orthogonal array that I showed you a little bit earlier. So in coding theory, the way these arrays are used is coding theory is interested in the rows. These rows, they're words for a person in coding theory. A word that may be transmitted through some noisy channel and received at the other end of the channel, maybe with some errors. Maybe exactly as transmitted. Maybe if this word is the one that's transmitted, the one with 4 zeros here, then maybe at the other end it's received as 4 zeros. But it could also be that there's maybe an error in transmission and that's received as 0001, let's say. And so a coding theorist then would like to have a code, and this is not a good one, would like to have a code where even if there's an error, that maybe somehow can recover from that, right? Can correct that error by maybe saying, okay, this is what I received, I don't see this in my code, But, well, here's the word that's closest in my code to the one that I received. Let's translate it by the one that's closest to it, and hopefully that's the word that was indeed transmitted. So, so in terms of coding theory language, what we have is we have 8 code words. They're of size. So the length of the code word is equal to 4. K is equal to 4 here. It's an alphabet, which is the number of symbols in the statistical language, of 2, and it's quite often actually these codes use s is equal to 2. And then there's something called the minimal distance, which is what a coding theorist is interested in. Like I said, the coding theorist would be interested in, how far are these words in the code apart? In some sense, you like those words to be further apart, because then you can make an error, and if it's received as an error at the other side, you can recover from that, because there's nothing else that comes very close to it except the word that was transmitted. So the minimal distance for this particular code would be equal to 2. And the minimal distance is defined as you look at the distance between any 2 words. For example, the first, well, I have 2 in blue here, the second one here and the 5th one. So they have a distance of, that differ in this entry and the differ in the first entry. They have a distance of 2, a Hamming distance of 2. And so if you look at any pair, you compute the distances, and the minimum of all those distances, that's the minimal distance of the code. So d is equal to 2 for this particular code. And ds2 is not very good, because if you have a code with a minimal distance of 2, then you can correct up to this many errors, and that's 0 in this particular case. So you it doesn't have any power for correcting anything. But that's the difference, right? I mean, for coding, we're interested in how far are these rows apart. And when we're looking at orthogonal arrays and statistics, we're looking at the columns. We're looking at properties that any t columns have. So that's not the same thing. In addition, the question that a coding theorist would probably be interested in is, you tell me how many columns there are, what minimal distance I want, and how many, what the size of my alphabet is, then he would want to know what is the maximum value of code words that he can use. You always like to have a code that's as large as possible, given those constraints. And that's, of course, again, different from what a statistician wanted, because a statistician, thinking of runs, wants to have the minimum number of runs that achieves certain things. So these things go in completely different directions, and it would seem to be very different problems. Nonetheless, there's a lot that's in common to what a coding theorist is interested in, and what a statistician is interested in. And statistics has benefited greatly from some of the research that has been done in coding theory. Let me try to explain in what ways. So let's first talk about linear orthogonal arrays, or linear codes. And we talk about a Galois field over a Galois field S here. The rows in a linear code or orthogonal array, they form a vector space. That's the definition of linear. And in statistics, many of you have heard about regular fractions. Well, regular fractions are either linear orthogonal arrays, or they are translates of the linear orthogonal arrays. Now, of course, if you have a linear code, then then you must have that the number of rows is a power of the number of symbols, of s. And so it's going to be a code that is of this form, where this is the number of columns, this is the number of rows, this is the minimal distance, and this is the alphabet size. Now, since this is a vector space, I can look at C as a matrix. I put all these words, I look at this as a matrix, and so I can look at the null space corresponding to that matrix. Well, that's the code itself, and it's a linear code again. In fact, you can easily show it. It's a code with the same length. The words are exactly the same length. It's the orthogonal complement of the code C, so the number of words is s to the k minus n rather than s to the n. And the same alphabet, and some minimal distance, and let's just use a new letter for that. Let's call it dperp. So cperp is, if you want, the dual code of the code C, and we have introduced the letter dperp to denote the minimal distance of cperp. So it turns out that if C is a linear code over GFS with dual distance dperp, then its code words actually form an orthogonal array of strength dperp minus 1. So if you want to assess how C does as an orthogonal array, it is not the minimal distance of C that you need to be interested in. It's the minimal distance for the dual code that you need to be interested in. And that minimal distance is related to the strength in this way. The strength is this dperp minus 1. And this was already realized a long time ago by Kempthorne, who, by the way, is a graduate of Clare College here at Cambridge. And there's a converse statement to this as well, namely that if C is an orthogonal array with strength T, and if T is the maximum possible strength of that orthogonal array, then it follows, and it's linear, then it follows that the dual distance for C is equal to T plus 1. So that converse was completely formulated by Bose. I mean, Kempthorne didn't formulate anything in terms of coding theory. He wasn't thinking about coding theory, but Bose made the connection between coding theory and fractional factorial experiments. Okay, so that's an important relationship. And one thing that opens up, of course, is that I can look now at codes and look at linear codes at least, and look at the duals of those linear codes, the cperp, find out what dperp is, and see whether these codes give me interesting orthogonal arrays. And there are many examples where that indeed happens, where looking at codes gives you very interesting orthogonal arrays that in some cases that were not known before. So in statistics, for a linear orthogonal array, or for one of its translates, this number dperp is actually called the resolution of the orthogonal array. So there's an immediate relationship there again between the concepts that come up in coding theory and that come up in statistics. Statisticians also study the length of the words in cperp through the so-called word length pattern, where bi, for I between 1 and k, is the number of words in this code cperp with I non-zero elements, meaning with Hamming distance I to the all 0 run. And we'll see in just a moment that that's something that also comes up in coding theory. Coding theorists are interested in this as well. Minimum aberration criterion selects designs based on these BIs. They sequentially minimizes B1, B2 to BK. So, usually if for example, if you're thinking about resolution 3, then you want B1 and B2 to be equal to 0. You want B3 to be as small as possible. And among all the arrays that have the minimum B3, you want B4 to be as small as possible, etc., etc. So you do this sequentially. And there's a nice paper that actually looks at generalized minimum aberration by Cheng and Tang in 2005. So these BIs are also of interest to coding theory, as I'll show you in just a moment. So linear codes, as already mentioned, can lead to very interesting orthogonal arrays. But then, is there a connection that extends beyond linear codes? I mean, is there something where maybe statisticians can benefit from work in coding theory that goes beyond just looking at linear arrays? And the answer is yes, there is. And you have to introduce some tools and some terminology. So let's take an arbitrary code now. No longer linear, no longer over GFS, arbitrary code. Pick a word in that code, let's say U, and define the weight distribution with respect to that word in the following way. AIU denotes the number of words in the code C with a Hamming distance of I to U. So you pick that one word, and you go through your code and determine, okay, what's the distance of this word to the one that I picked? What's the distance of this word to the one that I picked? And so some of them will have a distance of 1, some of them will have a distance of 2, and so on. And you just compute how many are there with distance 0, with distance 1, with distance k. That vector is the weight distribution with respect to u. Now you don't just do that for one word in the code, you do this for every word in the code. And then you take averages. And that's what we call the AIs. So that's the weight distribution of the code. No longer of one word, but of the code. Now for linear code, it turns out that these AIUs, they are the same for all u. So no matter which word I picked, the AIUs will all be the same. And of course, if that happens, then if you take these averages, then you get nice integers over there because all these AIUs are the same. For any code, whether linear or not linear, it holds that if you add up these AIs, it adds to capital N, to the number of rows in the code. It holds that A0 is at least equal to 1. Most of the time in coding theory, one would have A0 is equal to 1 because one wouldn't repeat any words. But in statistics, if you think about an orthogonal array, then yes, sometimes we actually repeat a particular run, a particular row. So we want to allow for that possibility here. So we have A0 is more than or equal to 1. And if the minimal distance is equal to d, then A1 to AD minus 1, they're all equal to 0 by definition of what the minimal distance is. And all the other AIs are, of course, positive. So this last statement here is true for any code, no matter whether it's linear or whether it's not linear. Now there's something nice called the weight enumerator of a code. And it's a homogeneous polynomial in two unknowns, x and y, so of degree k, as you can see. And the coefficients are exactly the elements of the weight distribution of the code, the AIs. And the nice thing is that for linear codes, there's a relationship between this weight enumerator for the code C itself and the weight enumerator for the dual code, C perp. So this holds for linear codes. And it's this relationship. Comes from Jessie McWilliams, who was also a Cambridge graduate, and I think she may actually have met Cantorn here because they had some overlap, but I'm not sure whether they knew each other or not here in Cambridge. But so what it does is it tells you the weight enumerator for the dual code in terms of the weight enumerator for the original code. And now remember, so just as we had a weight distribution for the original code, there's a weight distribution for the dual code, let's say A0 perp to AK perp. So the coefficients of the polynomial here can be equated to coefficients of the polynomials over here. That means that these AI perps can be expressed in terms of the AIs. And you can actually do that explicitly in this way. So AI perp turns out to be equal to this function of the AIs, of the AJs, and it's related to Kraftschuk polynomials, and it doesn't really matter for this talk what those are, but the only thing that matters is you can express these AI perps in terms of the AJs. Now this is true for linear code. What also holds, simply by definition, is that the sum of these AI perps are equal to the number of rows in this dual code, s to the k over n, over s to the lowercase n. A0 perp is equal to 1. These fellows are again equal to 0, because d perp is the minimal distance of this dual code. And all these other guys are non-negative. But this is true, again, I've just done this for linear codes. What if the code that we started with is not linear? Now remember that this I can do here for any code, right? I mean, there's no problem there. It doesn't have to be linear at all. But then this relationship here, I mean, I don't even have a C perp if the code is not linear. I don't even know what C perp means if my code C is not linear. Well, so the punchline of this is that if C is an arbitrary code, then there is no C perp, but I can still define the AI perps by this McWilliams identity. I can still simply define my AI perps in this way, even though there's no code corresponding to them anymore. And what you can show, and that comes from theory by Delsart, is that the properties that I showed you, for example, these properties over here, they still hold, even if the original code is not a linear code. So these properties remain valid. That's really what the linear programming bound is based on. The linear programming bound for orthogonal arrays. It says given the number of columns k, the number of symbols s, and the strength t in an orthogonal array OA NKST, it must be that the number of rows n is at least equal to NLP, where NLP is a solution of this linear programming problem. Minimize the sum of the AIs, right? We know the sum of the AIs is going to be equal to the number of rows in the orthogonal array, so that's what I want to minimize. Subject to, well, here are those conditions that I showed you earlier that all of the AIs must hold for every code. And now I define the AI perps through the McWilliams identity, whether it's a linear code or not, and it turns out these AI perps must satisfy these inequalities. So this is a linear programming problem just in terms of these AIs, because the AI perps can be expressed in terms of the AIs. This is just a convenient way of writing up these constraints, but these are really constraints in the AIs. And so solving this linear program gives you a bound for the number of rows in an orthogonal array, and it turns out that that bound is always at least as good as Rouse bound, and often better. So it does better job than Rouse bound. I still like Rouse bound because Rouse bound gives me a very nice explicit expression for what the bounds are. Linear programming bound, I have to run this linear program every time to find out what the bound is. You can also use these AI perps, by the way, to define a concept of generalized minimum aberration, extending it not just to regular fractions, and that's what Zhu and Wu did in 2001. And they also extended it further than that to something called mixed orthogonal arrays that I'll talk about in just a little bit. Yeah, this is running way too fast, I think. So I think many people know about Hadamard matrices. There's a close connection between Hadamard matrices and orthogonal arrays. If you have a Hadamard matrix, so a Hadamard matrix is a matrix of plus ones and minus ones, square matrix, such that all the columns are orthogonal to each other. And it's known that they can only exist if it's a 1 by 1, a 2 by 2, or a 4u by 4u matrix. And of course, the famous conjecture is that they exist for every multiple of 4, which I think most people would probably be willing to believe, but nobody has been able to prove. Due to invariance properties, you can always write such a Hadamard matrix in this form, making the first column a column of just once. And if you then pick what's left here, this matrix A, that's an orthogonal array of strength 2 with the maximum number of possible columns, namely n minus 1. In addition, and most people are familiar with that as well, there's a fold-over method. You take a Hadamard matrix, any Hadamard matrix, no matter how it looks like, and put minus that Hadamard matrix below it. And if you now look at this matrix over here, that's again an orthogonal array, and now it's an orthogonal array of strength 3 that also meets Rouse bound, so it also has the maximum number of columns. So these are very simple constructions, very simple relationships between Hadamard matrices and orthogonal arrays. They're very useful in statistical applications because they correspond, of course, to, and I'm not using 0 and 1 now, I'm using minus 1 and plus 1 as the symbols. They correspond to 2 symbols, and 2 levels is in statistical applications is quite popular, and it's used very often. So these relationships have been explored extensively. Perhaps a little bit less known is a generalization of that idea, and this refers to what are called difference schemes. And I'm talking about difference schemes of strength 2 here. So it's a matrix, DRCS, R rows, C columns, S symbols, based on an abelian group, G, of size S, with the property that if you look at any two columns, and you look at the element-wise differences of the entries in those two columns, then you'll see every element of that group appear equally often as a difference. So if I would pick, for example, let's say the second and the third column over here of this example, I look at the differences, 0 minus 0, and I'm doing this modulo 3. 0 minus 0 is 0, 2 minus 1 is 1, 1 minus 2, that's 2, 2 minus 2 is 0, 1 minus 0, that's 1, 0 minus 1, that's 2. I'll see 0, 1, and 2 will all appear exactly twice. And that's not only true for these two columns, that's true for any two columns that I pick. I see all of those differences come exactly twice. And that's what's needed for a difference scheme. That's a definition of a difference scheme. Now it's clear that the number of rows has to be a multiple of the number of symbols, because if I look at these differences, every element of the group has to come equally often, let's say lambda times, so the number of rows has to be lambda times S. That's called the index again. The Hadamard matrix is actually an example of a difference scheme, except I'm using a difference here that suggests that I'm using an additive notation, except with the Hadamard matrix it's a multiplicative group of two elements, so it would be multiplication rather than addition. But it's a different scheme, n by n, based on two symbols. So both of these examples that I've shown you here, the number of columns is exactly equal to the number of rows. Well, in general, that's not necessarily the case. But you can show that the number of columns can never be more than the number of rows. The number of columns must be less than or equal to the number of rows for such a thing to exist. And it's called a generalized Hadamard matrix if the number of rows and columns are the same. Now, what's the relationship between these different schemes and orthogonal arrays? It's a pretty simple one. If you take such a different scheme D and you add 0 to every element of the different scheme, and then you add 1 to every element of the different scheme, and then you add S minus 1 to every element of the different scheme, and you juxtapose all these arrays that you obtain, that's an orthogonal array. It's an orthogonal array of strength 2. So a different scheme, just by developing in this way, leads to an orthogonal array of strength 2. And in fact, you can always add at least one more column to it, and sometimes you can add more columns to it. So this is a fairly simple way of constructing orthogonal arrays, and it can, depending on whether you start with a good difference scheme, it can lead to good orthogonal arrays. Good meaning having many different columns. You can extend the idea to different schemes of strength T to get orthogonal arrays of strength T. I'm not sure that's very powerful. Hasn't been studied very extensively. So that would be one area, I think, where some additional research could make a difference. Here's a little table about the existence of different schemes, giving the, as far as I know, that's the question mark here, as far as I know, the best values for the number of columns for different schemes. So you see with two symbols, if lambda is 1, then the best value is 2. If lambda is 2, so remember the number of rows is lambda times S. So if lambda is 1, then we're talking about 1 times 2, S is equal to 2. 1 times 2, we're talking about 2 rows. This is a 2 by 2 matrix. Here we're talking about a 4 by 4 matrix. Here we're talking about a 6 by something matrix. Well, it turns out that 2 is the best you can do. You cannot have more columns than 2. If you have 8 rows, 4 times 2, then you can take a Hadamard matrix with S is equal to 2, so you can get 8 columns. With 5, lambda is equal to 5, so 5 times 2 is 10 rows. Turns out you can only get 2 columns. That's the best you can do. So the numbers in blue here, those are all generalized, well, either Hadamard matrices if S is equal to 2 or generalized Hadamard matrices if S is more than 2. And they're known to exist. The numbers in black, they're known to be the best possible values. And you see they're all very small, 2, 2, 2, 2, 2, but you can't do better. It's known that you can't do better. The numbers in red, these are the best known values for these particular cases, but it's not known whether you can actually do better. There may be constructions where you can do better. So it would be nice, again, to come up with some new constructions, some new ideas to construct these matrices and maybe get something better, or prove that you can do better than those numbers. So there's definitely still some work to be done there. There's quite a few things that we don't know about these different schemes. Mixed level orthogonal arrays. There are many open problems for mixed level orthogonal arrays. So a mixed level orthogonal array is exactly the same thing as an orthogonal array, except now if you take different columns, you might have a different number of symbols for each of the columns. So it's no longer restricted to having S symbols for each column, but you may have S1 symbols for the first column and S2 symbols for the second. But the idea of having a subarray, an n by t subarray, and seeing everything that could come appear equally often still applies. That's still the definition of an orthogonal array. They're important in statistical applications because you could have factors with different numbers of levels, but there's actually no coding theory equivalent. Coding theory this is not a problem I think is of that much interest to coding theorists. Rouse bounds, they can be developed very easily. They still, they look different, but the idea is exactly the same. Constructions are typically more challenging because you're now dealing with different numbers of levels. You cannot just go to one Galois field or a projective geometry based on some prime power S. So you have different numbers of levels now. So these things tend to become more difficult. Let's see. There's an extension of the linear programming bound for mixed orthogonal arrays, and I'll just leave that. Given the time, I'll just leave it at that statement. You can extend it. So and again, it's always better than Rouse inequalities. Zhou and Wu define generalized minimum aberration for mixed orthogonal arrays, so that can be done as well. But there are lots of open questions. And here are some of them. Very simple case. So I have one factor with m levels and k factor with 2 levels. And I'd like to know how many runs do I need in order to build such an orthogonal array. And I'm taking a very simple case here. I'm taking m is equal to 3. Well, it turns out if the number of runs is equal to 12, then the best you can do for k is 4, which is far off of the bound given by Rouse inequalities, which is n minus m, so it's 12 minus 3, it would be 9. You can't do better than 4, it turns out. And it's in blue because it's known that you really cannot do better. You cannot have 5 two-level factors in such an array. If you have 24 runs, n is equal to 24, with m is equal to 3, then it's known that you cannot do better than 16 two-level factors. Again, stays away from Rouse bound, but it's known that you can do better. So Rouse bound you cannot attain equality in Rouse bound. That's all that it means. For 36 runs, m is equal to 3. You could hope for 36 minus 3 is 33 two-level factors, because by now we have to expect that we can get there. The best known is 27, but it's actually not known whether you can do better or whether you cannot do better. So it's not known whether you can get 28 or 29, open question. All of these blue numbers, to the best of my knowledge, are open questions as to, sorry, all of these black numbers are open questions as to whether these are actually the best numbers that you can get. In some cases you do fairly well. There's a number of cases where the difference between is equal to n minus 8, number of runs and the number of two-level factors that you can get. That the difference is equal to 8, I should say, like here, like over here. But there are other cases where the difference is much, much larger, and where there's perhaps likely that you should be able to do better, but nobody has been able to come up with something better than what's shown in this table. There's another table that shows a similar picture where, again, we take only one of the columns with something else than 2 levels, k columns at 2 levels, and 1 column at n over 4 levels. You do very well if n is a multiple of 16, then these numbers actually do attain Rao's inequality. You know that you can do better there. Those can all be constructed. There are some others where we know that we cannot do better, but they don't attain Rao's inequalities. And there are some of these that do really very poorly, where you have 100 runs, and you can only come up with 22 2-level factors. So there's a lot to improve there. So there's a lot of, even for the simplest situations, as here, where you have only one factor that is not at 2 levels, there's relatively little known about the existence of these arrays and how many 2-level factors that you can accommodate in these arrays. Let's see. I'm almost done there, right? So I'm going to go very quickly over what we have here. This is the lattice of n1 orthogonal arrays, and I'll show you a picture that you can't read. The idea there is that tell me what number of runs you want to use. And this is a picture that is for 12 runs, so 12 rows. And the question then is, okay, if I know that you want to run 12 rows, can I tell you which orthogonal arrays you could use? Which are the orthogonal arrays that exist for that number of runs? And so this picture shows all of them. This is 2 to the 11, that means 11 factors at 2 levels. This is 2 to the 10 factors at 2 levels. And of course, if I know 2 to the 11 that exists, I don't have to know that 2 to the 10 exists. That's automatic, all right? And so that's a structure that you can build. Something called an expansive replacement method. You only have to know the arrays that are closest to the top. This one, this one, this one, and this one. And once you know those 4, then you can get everything else from that. So those things have been called dual atoms in this lattice of 12-run orthogonal arrays. And so the question is, can you identify all the dual atoms? In this particular case, there are 4, the 2 to the 11, the 3 to the 1 times 4 to the 1, a 2 to the 4 times 3 to the 1, and a 2 to the 2 times 6 to the 1. Everything else can easily be obtained from those 4 arrays. And so the question is, can you do this not just for 12, but can you do this for other numbers as well? And here are some examples where this lattice is completely known. Of course, the smaller cases are not that difficult, but it quickly runs into, or can run into difficulties. This was actually quite a bit of work to obtain the lattice for 64 runs. These two over here for 24 and 28, they have only recently become available by a complete enumeration of the number of the orthogonal arrays for 24 and 28 runs. So by computer program, Schoen, Eendebak, and Nguyen were able to identify all possible arrays for 24 and 28 runs, but their computer program can go further than 28, so it's just difficult to do by computer to enumerate all of this. I think the smallest unresolved case, if you want to have a crack at it, is n is equal to 36. So you can try to come up with all possible orthogonal arrays, at least with the dual atoms, because that will give you everything for 36 runs. Okay, you can go a step further. You can talk about non-isomorphic orthogonal arrays, so I have some references about that here. There's something here about orthogonal arrays for computer experiments, and there are many of you in the audience who know much more about this than I do. There's something about using orthogonal arrays for the construction of Latin hypercube designs. And there is something about nested orthogonal arrays for situations where you have experiments that, where you combine low accuracy experiments with high accuracy experiments, or maybe physical experiments with computer experiments. There is something called sliced orthogonal arrays, which has fairly recently been proposed in the literature for dealing with situations where you have both qualitative and quantitative factors in your experiment. And then I have some pages on, I'm going to go through this very quickly, so if you want to read more about it, you can read more about it yourself. Then I have some pages about some extensions, some variations on orthogonal arrays. One is semi-balanced arrays, which are defined in a similar way as orthogonal arrays, except that you're no longer demanding that every t-tuple is seen equally often as a row, but just every set of size t has to be seen equally often as a row. Don't care about the order, just the sets of size t, the t sets. You should see them equally often as a row. And those arrays have proven to be very useful in a variety of experimental settings, with crossover designs or with situations where there's a correlation structure within blocks, and also in situations where you have interference from neighboring plots within blocks. There's something called ordered orthogonal arrays, which is a generalization of orthogonal arrays. And in ordered orthogonal arrays, you have columns that are grouped, in this case, two groups. I don't demand, for ordered orthogonal array of strength 2, I don't demand that every two columns are orthogonal to each other. But what I do demand is that the first two columns in the first group are orthogonal to each other, and they are. The first column in the first group and the first column in the second group have to be orthogonal to each other. And the first two columns in the second group have to be orthogonal to each other. So the order of the columns becomes very important here. That's for the simple example, that's the definition. You can read the definition in general. And why these ordered orthogonal arrays were introduced because there's actually a relationship between these things and nets, TMS nets, and TS sequences in base B or Sobel sequences of B is equal to 2. Turns out that these TMS nets in base B, they exist if and only if a certain ordered orthogonal array exists. And so that's why people are interested in studying ordered orthogonal arrays. As I said, special case of ordered orthogonal arrays are the regular orthogonal arrays. Then one other thing I have here is balanced orthogonal multi-arrays. And well, here you see a balanced orthogonal multi-array. And what you need here is that the entries can be sets. They no longer have to be just numbers. And so here there are sets of size 2 for this column also, for this column also, and here are just sets of size 1. If the sets are of size 2 or more, then within a column, these sets have to form the blocks for a balanced incomplete block design. If they're of size 1, all that you need is uniformity. Every element has to come equally often. If you look at two columns, you need this orthogonality property. So if you check, for example, 0, 0, well, 0 and 0, they come together here in this row. They come together somewhere up there, the very first row, twice. Well, if you pick any other two elements, you should see them appear together in a row equally often. So it turns out that if all the sets are of size 1, then such a balanced orthogonal multi-array is simply an orthogonal array. So it's a generalization of the concept of orthogonal arrays. It was introduced for applications in sampling, for estimation of the variance of complicated functions when you're doing stratified sampling. And so there are questions about the existence and bounds for these balanced orthogonal multi-arrays. There are some things that I haven't spoken about at all. And the conclusions then, very simple conclusion. OAs have been studied extensively, but they remain an active area of research. And I think even though I have gone very quickly over a lot of my slides, I hope still that I have been able to convince you a little bit that there's a lot of work still to be done on orthogonal arrays, existence and bounds, methods of construction, enumeration, arrays with additional properties, and several structures closely related to orthogonal arrays. And I think it's time for wine. Right?
time has moved on. There clearly is time for informal discussion outside, and I guess that is what we should move to now. But I just want to thank John again very much for a very clear talk to me as a complete outsider. It was extremely clear, but the thing I have no real instinct for is how it plays into the design and analysis of experiments, but that's what you guys all understand, I guess. So I won't even ask the question. John, thank you very much, and let's all go outside. That's great. Thank you very much indeed.